So in this exercise, we're going to focus on the mechanics of intramedullary nailing. This would not be complete if we did not reiterate a little bit on the history of nails. Now, if you look at this array of nails, you can see that we started with the Küncher nail, which is a nail which acts by interference between the nail and the length of the diaphyseal bone. So the tighter the nail, the better the stability. And this becomes more tight because this nail is slotted. Okay? The next development, and you can see this is a femoral nail because of the anterior bow, is also a slotted nail, but the diameter is larger, and we have the possibilities of locking with locking bolts. And as you can imagine, if we lock, then we increase the stability, and we can influence the angulation, we can influence the length of the bone. This is a non-cannulated steel tibial nail, which is usually used in an unreamed manner. It is very thin, but since it is solid, it is also very stable. The next development for the tibia was what we call an expert nail. Why? Because we can now also apply this nail to very distal fractures and very proximal fractures. This nail is slotted in order to put down a guiding wire. This helps us with the reduction, and it is also made of titanium. Another development is a new type of femoral nail. You see the anterior bow. This is cannulated. It is not slotted. It is more or less solid. So it is very stable. It also has the possibilities of distal and proximal locking. This is what we call the proximal femoral nail. This can be used in different length. Also has the advantage of being able to be locked distally. This also has a design where we can fix this nail to the intramedullary canal of the femoral neck. So we have cephalomedullary stabilization for proximal femoral fractures. So these are elastic nails used in pediatric fractures. As you see, they're about 3 millimeters in diameter, and they also have a curved tip, which facilitates placing the nail inside the intramedullary canal of a bone which may not be very straight. Now, the purpose is to put in at least two, and they have to cross each other. And by crossing each other, you increase the stability, not only in the different axes, but also in the rotational axis. Now that you have seen what types of nails that you can apply to a bone, let's look at the biomechanics of nailing. And we will just demonstrate the different things that a nail can do or not do, depending on how you look at it. Now here, we ostensibly have a nail which is too thin, meaning the diameter is not sufficient in order to facilitate stability within the diaphysis, you see. It is not only too thin, but it is also too short and cannot be locked. So you see, we have automatic shortening as soon as we load the bone. Now we have increased the thickness of the nail, and the diameter now facilitates more contact between the bone and the nail. And this contact, the more contact we have, the more stable situation we have. Here we have a construct where we have a fairly small diameter nail, but what is different now? The difference is that it is locked proximally and distally by locking bolts. And this locking serves to stabilize the length of the bone. As you can see, there is no way that the length of this bone will be changed because of the locking mechanism of the nail. But still, there is maybe more instability that we would like to have. And this is because of the smaller diameter of the nail. If we increase the diameter of this unreamed nail, then we will increase the contact between the bone and the nail, therefore increasing the stability. And we can increase the stability even more when we ream, because when we ream, we can use a nail which even has a larger diameter. And this serves for more stability because we have more contact from one end of the bone to the other. Now, if we're dealing with fractures that are more unstable, you see what happens if I tend to use a nail which has a smaller diameter. There is more instability in this B-type fracture because the nail has a very small diameter, even though it is locked. Now this may heal, but this may take longer than needed. If we use a larger diameter nail and lock this in this B-type fracture, you see the stability increases. And as the stability increases, we rely on the indirect bone healing because of the micromotion here for the bone to heal. Here we have a situation of a C-type fracture, meaning comminution in the diaphysis. And the comminution is demonstrated by this little net. Now, this nail has an ideal diameter, and it is locked proximally and distally. What happens if I want to dynamicize this nail? By taking out the static bolt. Now if I let the patient load, which I would like to, this is what happens. So now I want each of you to take one of these models and just play with it so that you yourself can see the advantages or disadvantages of the nail design and the advantages or disadvantages of the locking mechanism. Here's the locking. Go ahead. You can look at the B-type fracture and you look at the C-type fracture. And go ahead and take out the locking bolts, proximally the static locking bolt, and see what happens to the fracture when you manipulate the fragments. So now let us discuss the results of this exercise and what you can learn.
In the online faculty support packages, you can find faculty guides for each station and, where appropriate, topics for discussion and frequently asked questions. In case of questions, please send an email to templates@aotrauma.org.